Welcome. Question 4. Use the triangle method to sketch the plane x minus 6y minus 2z is minus 6. Okay, so what we have to do here is find points on each of the 3 axes. So when y is equal to 0 and z is equal to 0, and then we clearly have x is equal to minus 6. So we have minus 6, 0, 0 as one point. That is on the x-axis. Okay, now when x is equal to 0 and z is equal to 0, then we're just looking at this. Minus 6y equals minus 6. Well, clearly that gives us y is 1. So we have another point, 0, 1, 0. And then finally, when these two are 0, 0 there, 0 there, well, dividing that equation by minus 2 gives us z is equal to 3. So we have 0, 0, 3. Okay, now we've got 3 points on each of the axes, so we can draw the axes and those points and then fill in a plane. So x-axis, y-axis, z-axis following the right-hand rule, x, y, z. Okay, so it comes out like this. Now, first one, that's minus 6, so I have to go out here. 1, 2, 3, 4, 5, 6. So that's out this way in the negative direction. Okay, this point, well, it's right there. And then this point, that's 3 up on the z-axis. So 1, 2, 3, and we'll put that there. Okay, now what we do is fill in a triangle between those. And then if you really want to, you can then imagine a rectangle that includes that triangle on the same plane. So I don't know, something like this, right? All right, moving on. Find the scalar equation for plane through the point, 3 points, 1, 0, 0, 3, 5, 1, and 4, 2, 0. Okay, so let's just imagine. Now we can see here that this is not going to be vertical, so the coefficient of z will be non-zero. So since plane is not parallel to the z-axis, the coefficient of z in ax plus by plus cz equals d has c not equal to 0. Right? That's useful because we have 1, 2, 3, 4 coefficients here, right? And so in this case, I can take this equation and divide throughout by that coefficient and get a over cx plus b over cy plus z is equal to d over c, right? And then I can rename these coefficients uppercase letters. So we can assume, without any loss of generality, and I'll write that w log without any loss of generality, that z is equal to, say, uppercase ax plus uppercase by plus, say, uppercase c. So of this form, right? Because we can divide by the coefficient of c, assuming it's non-zero because it's not vertical. Okay, so we have something of this form. Well, that's great because now we have 3 unknowns and 3 points, so we should be able to solve a system. So let's go ahead and sub in and do that. So we've got using, so 1, 0, 0 gives, z is 0, so 0 equals a times 1 plus b times 0 plus c. Okay, well, what does this say? Well, that says that a plus c is 0. Okay, now let's use our next point. 351 tells us that 1 is equal to 3a plus 5b plus c. Okay, so we've got a second equation. Now, 420 tells us that 0 is equal to 4 times a plus 2 times b plus c. All right, there's a third equation. Now, we want to write this as a system of 3 equations and 3 unknowns. All right, so there's no b in this, so I'm going to write 1, 0, 1, and then here we've got 3, 5, 0. Oh, right, no, c is 1, yeah. Coefficient of c is 1. Okay, and then 4, 2, 1. Multiplied by a, b, c is equal to 0, 1, 0. Okay, so now I have a matrix equation that I can solve. So we've got a couple of options here: row reduction, Gaussian elimination, or taking the inverse of this matrix if it's got a non-zero determinant, multiplying that on both sides. Now I can quickly do this in Mathematica so I can spare you the actual details. You would have done this in a previous course, no doubt. Okay, so I'm going to enter a matrix, and this is how I enter it here: 1, 0, 1, 3, 5, 1. I'm just entering the rows, and then 4, 2, 1. And so I'll show you this. I can just say, show me this as a matrix, and it displays that as a matrix. All right, but meanwhile, I'm going to call this M. All right, and then we have another thing, the right-hand side of this, which I'll also enter, and let's just call this T. 0, 1, and 0. All right, and just to show you that it looks like it does on the page. Okay, here we go. All right, so what I want to do now is take the inverse, and I can just write inverse of the matrix M, right? So it looks like this. And then, you know, you could display this as a matrix if you wanted to, and multiply that by T. Okay, we get this, and then let's just display this as a matrix as well. And this is easy enough to do by hand, all right? So what this tells us is that ABC, so put dot, 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 do this by hand. Right, so by a Gauss-Jordan, for example. Okay, and we get ABC is minus 2 over 11, 3 over 11, and 2 over 11. Right, which tells us then that the equation of the plane is, now if we just take this and multiply everything by 11, we'll have 11z equals minus 2x plus 3y plus 2. Okay, so there's an equation of the plane, and if you divide by 11, you get those fractions there. All right, let's move on. Find the vector and scalar equations of the plane through the point. So let's call this P equals 403 and normal vector 0, 1, 2. And we've got to find scalar and vector equations for that plane. All right, so let's draw a picture, right? Think geometrically, prove algebraically. So here, let's imagine that this is our plane. And then here's this point P, and then normal to that plane is this vector n. All right, so just draw a right angle there. Okay, so what I want to do now, let's imagine that I have some other point Q, which is x, y, z, right? So I have this point Q. Now from P to Q, I can form another vector, say r. Okay, and so since r has to be perpendicular to that normal vector, by definition of a normal vector, it is perpendicular to that plane. So what we have then is that the dot product of n and r is equal to 0, right? So that's by definition of the normal vector, and since we've taken r to be parallel to that plane. All right, now r is equal to, let's see, it's p minus the coordinates of p minus the coordinates of q, but let's put pq, right? And remember, we reversed this. I said that the wrong way, but q, so q minus p, all right, or the coordinates of q, take the coordinates of p, and so we have x, y, z, subtract, and these incidentally here are vectors. They're position vectors, but they're taken from some origin to the point when you think of those as vectors. So that's why the coordinates match up with the vectors. All right, so minus p, 403. All right, now simplifying this, that vector r is x minus 4, comma y, comma z minus 3. All right, now let's take the dot product. So n dot r is 0, 1, 2 dot x minus 4, y, and z minus 3. Now that dot product is 0 by x minus 4 plus 1 times y plus 2 times z minus 3. Okay, so simplifying this, that part's 0, this is y, so we've got y plus expansion of this is 2z minus 6, and this dot product is 0, so this gives us the scalar equation of that plane. And incidentally, this is the vector equation, or one of the vector equations of that plane. But I think I'll give you another one in a moment. Okay, so this is our scalar equation, so let's write scalar equation, and let's rearrange that so that it says y plus 2z equals 6.